Hey there, we're back with a video about the meaning of the first derivative. We've gotten some glimpses about what the first derivative might mean when we talked about velocity, we talked about related rates, we talked about all these things. Now we're going to talk about how to use a derivative to analyze what a function looks like. All right. So we got three examples now. There are examples that go through multiple parts, and I'm going to lead you through three different types of functions that we might use a derivative to explain the behavior of that function at certain spots. Here we go. We go back a little bit to pre-calculus, and we're going to use the fact that, first of all, f prime of x1 equals the limit as x2 goes to x1 of f of x2 minus f of x1 over x2 minus x1. This limit right here should look familiar. This is how we defined the derivative way back when. And we're going to use this to explain, along with pre-calculus knowledge, how the first derivative relates to increasing or decreasing behavior. If you remember from pre-calculus, we said that a function was increasing if, as x gets bigger, the function values get bigger. So if x1 is less than x2, that means that f of x1 is less than f of x2. And here's a nice little picture of what's going on here. So as the x values get larger, the function values also get larger. It makes sense. That was what it means for this function to increase. As x goes up, y goes up. So if we apply this definition, all right, we would notice that f of x2 is bigger than f of x1. So going back to this limit definition up here, we would see that the numerator would be positive because f of x2 is bigger than f of x1. And we already know x2 is bigger than x1. That's kind of how we define this here. So our denominator would also be positive. So this whole limit will be a positive number. And that would mean that the derivative is bigger than 0 in order for a function to be increasing. A function decreasing if x1 less than x2 means that the function value at x1 is higher than the function value of x2. All right, so we can see that from this diagram right here. We have a higher function value at x1 than we do at x2. So as x goes up, y goes down. All right, so going back to our definition, f of x2 is the smaller of f of x2 and f of x1. All right, so we would get a negative number in our numerator and still a positive number in our denominator. So in order for a function to be decreasing, that means that f prime of x is less than 0 for every value in a certain interval. Some other definitions we'll need to know. A critical point is a point where f prime of x is equal to 0 or f prime of x is undefined. The critical points, as you might expect, are the points where it's critical for us to check to see whether or not the derivative changes signs from positive to negative. A stationary point is a type of critical point where f prime of x is equal to 0. All right, so we give it a particular name just because it's a point that indicates where the derivative is stopping. It's stationary for a moment, so the derivative is 0. And the function is monotonic on an interval if it does nothing but increase, you know, like a monotonic voice, right? It doesn't do anything, all right, but the same thing the whole time. So the monotonic function is a function that just increases or just decreases on a particular interval. All right, so here's an example. Suppose f of x is equal to x to the fourth minus 4x cubed plus 4x squared. We want to find where f of x is increasing and decreasing. So as we just pointed out, in order to find where something's increasing and decreasing, we need to find where the derivative is positive for increasing and negative for decreasing. So let's take that derivative. F prime of x is equal to 4x cubed minus 12x squared plus 8x. That's the power rule. And what we need to do is find our critical points. And our critical points are going to be put onto this thing that we're going to call sign test. All right. The whole idea is the derivative can only change from positive to negative or vice versa if there's a point where the derivative is 0 or undefined. All right. You're not going to jump from 2 to negative 2 all of a sudden on a polynomial, in particular if you don't cross 0, or in general if our derivative is not equal to 0 or is not undefined. So what we're going to do is we're going to take our derivative and set it equal to 0. We can see that we can factor right here. And a little bit of algebra tells us that this function is equal to 0 at x equal to 0, x equal to 1, and x equal to 2. Okay? So from here, we're going to do what we call a sign test to help our analysis. You may remember this from polynomials or rational functions. All of our critical numbers are going to go at the top, 0, 1, and 2. You'll notice I didn't test to see where the derivative is undefined because it's a polynomial. It's always defined. All right, so we put 0, 1, and 2 here. And then we're testing our first derivative. Is it positive or negative? So from pre-calculus, hopefully you remember that we want to test a number that's a little less than 0. Right? We plug in a number a little less than 0 into our factored form here. So let's say like -1. And all we're worried about is whether we get a negative or a positive out. So -1 times 4 is a negative number. -1 minus 2 is negative. -1 minus 1 is negative. So we have a negative times a negative times a negative. 3 negatives make a negative. I test a number between 0 and 1. All right, so like 0.5. I get a positive in the first part. 0.5 minus 2 gives me a negative. 0.5 minus 1 gives me a negative. So 2 negatives make a positive. I'm not going to do all these here. This would be something that we know from a previous class, but you'll notice that our signs go from negative to positive to negative to positive. Let's make our conclusions here. F prime is increasing wherever, or F is increasing rather, wherever F prime is bigger than 0, and this happens between 0 and 1 and 2 to infinity. And F is decreasing whenever F prime is less than 0. That's from -infinity to 0 and from 1 to 2. And I put the graph of the function right here, and it tells us that that's true. So from -infinity to 0, we see our function decreases, and also from 1 to 2, the function increases from 0 to 1 and from 2 to infinity. All right, some more terms that we want to review. A function has a local or relative maximum. They're interchangeable terms here. And x is equal to c if f of x is less than or equal to f of c for every x near c. So our c that we're talking about is this point right here at c equal to 1 in this particular diagram, right? And we call this a relative maximum because it's higher than all of the other points that are around it. A function has a local or a relative minimum at x equal to c if f of x is bigger than or equal to f of c. So f of c is the smaller of any values that are all around it. And we see with this absolute value function at x is equal to 1, that's our c value here, we have a relative minimum. Notice the derivative is not equal to 0 for the second example. The derivative is undefined. And so that's why it's important we define critical points as points where the derivative is 0 or undefined, because those could be relative max or minimum values. How does this have to do with the derivative? Well, hopefully you've noticed that a function has a local maximum at x equal to c if the derivative goes from positive to negative. The slope of a function is positive and then it's negative. The function increases and then it decreases. A function has a local minimum if f prime goes from negative to positive, right? Negative slope, positive slope at a particular point. As we'll see, however, we can only have relative extreme at critical points, right? Otherwise, the derivative is not going to change sign. We can't go from negative to positive unless it's a critical point. However, not every critical point is a relative extremum. So for example, with y equals x cubed, the derivative, if you work that out at x equal to 0, is 0, but it's clear that we do not have a relative maximum or minimum value at x is equal to 0 for the cubic function. So it's a critical point, more particularly it's a stationary point because the derivative is 0, but it is not a relative maximum or minimum value. All right, so let's finish up example number 1 here. All right, suppose f of x equal to x to the 4th minus 4x cubed plus 4x squared. We had already figured out our sign test on the previous slides, right? So all we need to do is notice what's going on with our derivative signs here. So we have a relative maximum where the f prime changes from positive to negative, right? That would be at x is equal to 1. We go from increasing to decreasing. And a relative minimum wherever f prime changes from negative to positive. So that's at x equal to 0. And at x equal to 2. And we can see that from our graph right here. Relative minimum value at 0 and 2, relative maximum at x equal to 1. Let's try another example here. So suppose f of x equals x squared minus 1 over x cubed. We want to find where f of x is increasing and decreasing and any relative extrema. Notice in order to find the first derivative, we have a quotient, x squared minus 1 divided by x cubed. So we do the quotient rule. I won't go through all the details of how to find that here. I'll assume you know how to do the quotient rule. We end up with 3x squared minus x to the 4th over x to the 6th when we simplify. So we find any critical points by finding where the derivative is 0 or is undefined. So f prime is equal to 0 whenever our numerator is 0, but our denominator is not equal to 0. So we set 3x squared minus x to the 4th equal to 0. Once we factor, we get x is equal to plus or minus the square root of 3. We also get x is equal to 0 technically, but that actually causes a different problem the derivative is undefined at this point because the denominator is also equal to 0 at that point. In any case, we get 3 critical points. X is equal to plus square root of 3, minus square root of 3, and 0. So now we perform our sign test. We need to choose a number that's really large negative, less than negative square root of 3. So like negative 1,000. Well, notice if I do negative 1,000, I'm going to square it, raise it to the 4th, and raise it to the 6th. Those are all even powers. All right. So, but however, I'm going to get a really large negative number in our numerator because the x to the 4th overpowers the x squared. So in other words, I get a negative here. A number between negative square root of 3 and 0, so like negative 1. All right, when I plug it in up here, I get a 3 minus a 1 over a 1, which gives me a positive number. And you can do the whole test as you go along, and you get a negative, positive, positive, negative when you work that out. So we did our sign test. Critical numbers are on the top. And we see that f is increasing whenever f prime is bigger than 0. So this is negative root 3 to 0 and 0 to root 3. We're just reading off the sign test. Decreasing whenever f prime is less than 0. So it's from negative infinity to negative root 3 and root 3 to infinity. Relative maximum whenever f prime changes from positive to negative at x is equal to square root of 3. That's right here. And relative minimum when f prime changes from negative to positive at negative square root of 3. So we can see from our graph, it's hard to tell. That's where calculus comes in, but we had a relative maximum at root 3 and a relative minimum somewhere right in here at negative root 3. So notice what happens at 0, by the way. The slope is positive on either side, and in fact, because of the original, we have a vertical asymptote at x equal to 0. And there's no sign change, so that tells us there's no extrema at that point. Last example here, suppose f of x is equal to x plus 2 sine of x. Find where f of x is increasing and decreasing in relative extrema, only on the interval 0 to 2 pi. So as always, find the first derivative. That's 1 plus 2 cosine of x. And we want to find our critical points by finding where the derivative equals 0 or is undefined. This function is not undefined anywhere. All right, so we set the derivative equal to 0. Those will be our only critical points. And we need to figure out where cosine of x is equal to negative 1/2. So if you're using that finger trick, all right, that would be our index finger, all right, which is the pi over 3 family. And where is cosine equal to negative 1/2? Well, that would be at 2 pi over 3 and 4 pi over 3. Okay, we do a quick sign test. A number between 0 and 2 pi over 3, let's just say pi over 3, we get 1 plus 2 cosine of pi over 3, which is a positive number. A number between 2 pi over 3 and 4 pi over 3, let's say pi. When you work this out, you're going to get a negative number, and then a positive number bigger than 4 pi over 3. Increasing wherever f prime is bigger than 0, we can see from our test between 0 and 2 pi over 3 and 4 pi over 3 to 2 pi. Derivative is positive there. Decreasing whenever f prime is less than 0, that's between 2 pi over 3 and 4 pi over 3. And then relative maximum, derivative changes from positive to negative, that's at 2 pi over 3. And negative to positive would be a relative minimum, that's at 4 pi over 3. So in summary, the first derivative tells us a lot about the behavior of a function. A positive derivative means the function is increasing. A negative derivative means the function is decreasing. And then whenever derivative changes from positive to negative, we have a relative maximum. For our original function, derivative changes from negative to positive, the original function has a relative minimum. Thanks for listening. We'll see you in the next video.